The logistic regression is zero hidden layer neural network. And in neural network, for each neuron, we call this linear combination and active function. This is the neuron, and we have to activate each neuron using activation function. That's the nonlinear part coming in. And what is a one hidden layer neural network? One hidden layer is you have one more layer between the input and the output. So here is an example of one hidden layer neural network. So you have linear combination of the input, and you do it 4 times, basically. And you have 4 neurons on the first hidden layer, and then you connect that to the output. The output layer is not the hidden layer. You directly connect to y-hat. So for a one layer neural network, if you write it out, what happened behind this, you have 4 neurons, then you need to do linear combination 4 times for the input x. X has 3 elements. It's a baby example. We have x1, x2, x3, 3 features. So you do linear combination of x1, x2, x3, and you get A1, you get Z1. Z1 is before you apply activation function, you get Z1. And then similarly, you can get Z2, Z3, and Z4. And then you apply activation function on each of these Z. So when you apply activation function to neurons, it's element-wise. You just apply the same function on each value on that layer. So then you get all the activated neuron, that's A1 to A4, and you do another round for linear combination, and you can get Z1 and do activation function, you get A1, 2. And here, since we only have 1 layer, this A1, 2 will just be the y-hat you'll have. So you can see in just for one sample, you can vectorize the way you calculate neurons. So you can basically vectorize all the A1 from A1, 2, 3, 4 to be a vector of A1. That's the first layer's neuron. And since we have M samples, so we need to do all of this for M samples to calculate. If we use stochastic gradient descent, we just update the parameter for 1 sample each time. You can just do this and loop for I from 1 to M. But it's not efficient. So more often people will vectorize the sample. So you don't use just single sample each time. You use a list of vector of sample each time. And if you use all the M sample each time, that's called batch gradient descent. And then if you use all the M sample, you can stack it up together. So X becomes a matrix and W is a matrix. So you do similar linear combination of each input, you do multiple linear combination, and then you do that for all the samples, M samples, and then A becomes a matrix, and then Z2 is a vector here because it directly connects to y-hat, so it's a 1 by M vector, and then you do an activation function of Z2, you get A2, and that's connect to y-hat. So if you vectorize this, that's what you get.